we discussed the design for the actions and the guards for the two new events, ILM and ILOut. And we now should be quite ready to talk about how we can formulate the proof obligations that would be associated with these two events that are actually introduced in the refinement model. Let's talk about it. But before that, let's do some very quick groundwork, which will be very similar to how we actually did it before we formulated other sequence. Right, so the first one here, very quickly, just about before-after predicates. You might have noticed that for our earlier events for ML in, ML out, either the abstract version or the concrete version, let me show to you very quickly. If you look at those events, you will see that over here, okay? You can see we only got one single action over here, right? They just happen to be the case. In general, you may have multiple actions using the colon equal becomes operator. It's definitely possible, right? That's exactly what we're seeing now. So I just want to point out to you, don't really assume you always only got one action as the actions for the particular events, right? Let me go back here. That's one thing I'd like to point out. And here we got two actions over here. We also got two actions over here. That's why I said multiple actions on the slides, okay? And the before-after predicate will be just the same as before. Let's just do some exercise together. Right? I'll let you pause the video right now, and you want to answer this correctly, precisely. Okay? There cannot be any missing predicates. What will be the corresponding before-after predicate for ILM actions and also ILOut action? Meaning that if they are taken as a state transition on the concrete state space, what would be the before-after state relationship? Right? Before and post states. Right, so what will be the before-after predicates? You can now pause the video and write down your answer. Alrighty, let's now compare your answer against mine. Okay, and apparently we can definitely write down, first of all, the variables that are actually mentioned in the actions. In this case, we mentioned A and B. So that means A prime should be equal to A minus 1. And, right, you always conjoin the before-after predicate for each individual action. And also, B prime is equal to B plus 1. However, for your before-after predicate to be complete, you must also address about those variables that they are actually not mentioned. In that case, A and B are mentioned but not C, right? You can see A and B are mentioned but not C. That means C is going to maintain its value between the pre and post states. So what I will do is I'm going to say, and C prime is equal to C, right? It's not mentioned. And hopefully you got it right. If you only got these two predicates, this conjunction over here as before-after predicate, it's not exactly right. And similarly, what would be the before-after predicate for ILOut over here, right? So following the same pattern, we're going to first of all write down the before-after predicate for those variables that are actually mentioned in the actions. So that will be B prime equals B minus 1 and C prime equals C plus 1. And what's really not mentioned is actually A, right? In that case, A is going to maintain its value between the post states and also pre-states over here, right? So that's about the before-after predicate I would like to emphasize before we actually start formulating the proof obligation. We're going to need that. Alrighty, and one more background I would like to talk about, but let's now go back to the slides first of all. Right, that's this slide over here I just mentioned about before-after predicate. You can definitely refer to it. And I want to revisit this particular diagram which we spoke about earlier, right? Remember last week when we tried to prove that the abstract events actually simulates its concrete counterpart. Well, the other way, you can think about for every concrete events that we have, we want to prove it being simulated by its abstract counterpart. You can go either way, right? So in order to prove it, we actually need this so-called commuting diagram. We want to make sure the pre-states are actually related by the concrete invariance, and also the post states. In the post states, both the abstract and the concrete are also related by the concrete invariance, with, of course, the variables value substituted by the effects of the abstract and concrete events. That's something we said last week. If you have any doubts about how to interpret this diagram, please go back to the last week's lecture and make sure you actually understand it. And we're going to say a little bit more about this diagram over here, which is, here is our issue. We are now talking about not really the events that actually exist in both the abstract and the concrete world, right? So for example, for ML out, In that case, you got ML out in the concrete level, you got ML out at the abstract level. That's good because you know exactly which events to really look into. But for our case over here, for new events, you simply, well, let's say the ILN. ILN is a concrete event that was newly introduced into the refinement model. But the problem is, there is no abstract counterpart for the ILN. Agree? Simply no, because ILN was only newly introduced into the refinement model. It simply doesn't exist in the abstract model. Right? So strictly speaking, every new event does not have an abstract counterpart. That's just a fact. Nothing we can do about it, right? Because in the refinements, it's always natural for you to also introduce new stuff, like a new events and new variables. So what should we do? Well, we're still going to reuse this fantastic diagram over here. We still want to really prove that your concrete events that's actually newly introduced will still actually preserve the invariant. That's our goal. But how can we actually find that abstract counterpart that doesn't actually exist per se? How do we do that? Well, the way we do it mathematically is by saying this. We're still going to think about there is some abstract counterpart, but that abstract counterpart is a very special event, which I'm going to show to you, right? So we say that every concrete new event, that's what it over here denotes. Every concrete new event is simulated by a special abstract event. You can think about for every new event, its abstract counterpart is exactly this particular new event, which I'm going to talk about. This particular abstract events, which I'm going to talk about. Right, so that one is called skip over here. Let's first of all get some intuition from the literal meaning of this skip events. Skip simply means whenever this event is enabled and it's allowed to occur. And when it's allowed to occur, it simply does nothing. It simply just skip about the updates it might potentially do to the state space. Right, so let's now talk about its simple definition. We call this a dummy event, meaning that it's like a dummy. It doesn't do anything useful. So it's non-guarded. You can see there's really no guard as if it's true. So it's always enabled. It also does nothing to the state variable. You can see in between the begin and end. So this is the very first event that we actually see in the lecture that actually has no actions between the begin and end. So that's why it does nothing. If the event occurs, the variable in the pre-states and the variables in the post-states, they remain exactly the same, right? It's why we said it's called skip. And about this non-guarded property over here, meaning that there's no guard, I would like to look ahead a bit, which is some discussion we're going to talk about after we prove the invariant preservation. So this is so remember, let's go back to our initial discussion for the initial model. So we said that whenever you got any events that should be that are supposed to be useful, it better be that the guards exist. It should be stronger than simply just true, right? Remember the first version of the MLL and MLN that we spoke about earlier. In that case, both events are simply non-guarded, meaning that they're always enabled. So what will be the consequence? For example, if you're able to keep executing the action for the ML out, meaning that the variable n is going to be kept incrementing. In that case, you can easily go above or go off the upper bound for the n variable, which will be d, right? So that's why we have to put some put some guard to make sure whenever you want to execute ML out, you better be that the current state variable n allows you to do so, right? So in the case of the normal events, if the guards are simply are not there, are simply absent, then it's very likely that you might the continuous occurrence of the same events may just violate the invariance. But in this case, you might argue that for the skip events, it simply does nothing. How can it do any harm to the invariance? Because remember, we always, when there's any state transition, we assume in the pre-states the invariant will be preserved. In that case, if the skip event simply does nothing to the state variables, the post-state should be guaranteed to still maintain the invariance. I agree with you. So, in the case of the skip events, the potential harm it might do to the system is not about invariant violation. It's about something else. That's something I will talk about later after we finish our proofs of the invariant preservation. But keep this in mind, and then you can even think about what kind of potential harm can the skip event really do to the system other than invariant violation. Think about it, and then we'll get to the deep discussion about it later. Right, let's go a little bit more bullet points, and then I'll switch to iPad to give you a little bit more visual connection between the diagram over here and also the skip event. We'll do that. Right, so what's the before after predicate for the skip events? Well, in this case, because it simply does nothing, so that means the post state value will just be the same as the pre-state value for all the variables. And for the skip event, in our context, we're talking about skip events at the abstract level over here, in which case we only got one abstract variable n, right? So that means n prime is equal to n. Right? It's a very straightforward derivation over here, and we're gonna need this skip event. It's before after predicate when we try to formulate the sequence for the invariant preservation proof obligation. We'll see that. Let's now talk about how we can fit the this dummy event skip into the abstract transition, especially how it actually simulates each of the new concrete events that we spoke about, right? That's something I'd like to do briefly. Let's now talk about the text over here. So we say each new state transition, in which case it will be either IL in or IL out, is going to be a transition from the concrete states over here. So you can think about over here, let's still make sure we understand this diagram properly. Over here. So this will be some concrete new event transition. Concrete new event transition on a concrete state, of course. And specifically, we'll talk about IL in and also IL out. IL in and also IL out. And over here, about the corresponding abstract counterpart, it will be this skip events that we just spoke about, the dummy events. So this will be the corresponding abstract transition. Abstract transition by the skip over here. And of course, in the pre-states and the post-states over here. You can think about in the pre-states and the post-states. So this will be the pre-states over here. And this part over here, V prime and also W prime. This part over here will be the post-states. Both of them should be related to by the concrete invariance over here, right? That part will be the same. So the only part that's a little bit different from what we studied before about the diagram is now the concrete transition is now being made by the newly introduced event that only exists in the concrete model. And the corresponding abstract events that will simulate the concrete transition will be the dummy events that we introduced called skip. That's the only part that's different, right? But it's still important to know that the pre-states and also the post-states, both of them across the two worlds, abstract and concrete, should be related to by the concrete invariance. Okay, and I'd like to do just a little bit of illustration as we did before. Remember the diagram we did about the state transition, right? When we actually try to compare the concrete transition versus the abstract transition with the concrete example, right? And to save our time, I'm just going to draw that in 1 second over here by copy and paste. All right, over here. So this is what we did before. I think that this might be very nice to really see exactly the two kinds of concrete events, how they can be simulated by their abstract counterpart. I think that'll be very important. For example, you can see in this case, we got ML out. So that's the concrete version of the events. And we got ML out over here. That's the abstract version, right? Let's just remind ourselves. And we say that this ML out over here, this abstract version, which simulates. So we can say simulating the concrete version, which is over here, right? That's a concrete version, right? And we say that the invariant number 4, you can definitely refer back to your notes about the concrete model. Invariant number 4 is the only invariant condition that actually involve both the abstract variable and also concrete variable. And actually it's here. Abstract variable n versus n prime, the pre-state and post-states, it should be equal to correspondingly a plus b plus c or a prime plus b prime plus c prime, right? That's what we learned from earlier. And now let's try to do one more transition, right? And if you actually try to look at the diagram, it corresponds to exactly our discussion just earlier, right? We said that for every ILN, there should be some corresponding earlier occurrence of ML out, right? Why don't we see that right now? Because after this initial ML out, we actually have one car that actually moved from the island into the bridge, basically, right? That's ML out. That's what we have. So that's why we got A has been incremented to 1, right? So that's what we have. So what I want to do is I want to just show exactly how things should go. So we got this initial ML out. So after that, we actually got, at the moment, A, the concrete variable, is exactly equal to 1, right? So A is now exactly equal to 1. And we want to do one more occurrence of the events, which will be the new events. Let's say this car over here, after a certain time driving along the bridge towards the island, let's say now they are now on the verge of entering from the bridge into the island, right? So this is going to be denoted by the occurrence of ILN, right? So that's what we want to do right now. Here's the ILN over here. In that case, we know that it's what it's going to do. It's actually specified by its action. So when we actually got this particular occurrence of the ILN, we're actually going to decrement the value for A and also increment the value for the island, right? But initially, right before that happened, we know that B over here is actually equal to 0, right? So I want you to notice this particular states over here, exactly over here, right? You can see after the initial ML out, we actually got only A being incremented from 0 to 1 and 0 and 0, right? That's exactly what's happening over here. But now we're going to have one more transition for that particular car. So that's the only car that actually going to enter into the island. Before the entrance, the island is simply just empty without any car. Let's now do this transition. So what we're going to do is as before, we're going to do the abstract transition first. Starting with this particular state after the earlier ML out, we're going to do island in. That's what we'll do. And then we're going to see what the resulting state is. And then we're going to perform the abstract events skip, which will simulate this particular abstract events. And then we're going to see what the resulting state is. And we'll make sure that concrete invariance will still be valid. You will still be satisfied in the resulting state. That'll be the plan. All right, let's take a look. So what we'll do is we're going to, first of all, perform a transition over here. That one is going to be, I'm pretty sure I can draw better. Okay, this one over here is going to be IL out. Oh, sorry, IL in. Beg your pardon. This one over here. Right, so it's going to be IL in. So the same car enters the island. And then what will be the resulting states? Let's just copy the pattern for this states over here. Right, let me just copy that. And then let's paste it here. I might just have to make it a little bit smaller. Maybe just like this. Right, it's still readable, hopefully. Right, so in this case, what should be the corresponding action, if you can recall? Right, the corresponding action will be for island in, we have to decrement A and increment B. That makes sense, right? So the car will get off the bridge and gets into the island. So we're going to say A will be decremented from 1 to 0. And B remains the same. Oh, sorry, B will be incremented, right? 0 to 1. And for C, the traffic for the other direction will remain to be 0. That's what we have. So the main thing we changed are two things. So there are two things we changed. Let me highlight them. So we actually decrement A and also increment B, right? So that'll be the concrete states. And what will be the corresponding abstract events that will simulate this concrete transition? It's going to be, as we said by definition, it's going to be skip. Again, it's going to be simulated by skip because we simply don't have, strictly speaking, any abstract counterpart for this newly introduced events at the concrete level in the refinement model. Right, let's now take a look. So what we'll do is, correspondingly, we're going to have this abstract transition over here, right, over here, and that one there is going to be skip, right? That's what I really want to show to you exactly how things will work over here. All right, so this will be the abstract transition, and according to our understanding about the abstract transition, especially its before-after predicates, what should be the effects on the states? We're going to talk about it in just a moment. So that'll be the resulting states, the post state at the abstract level. And we know that the before after predicate is simply n prime is equal to n, right? So whatever n is in the pre-state, which will be 1, in that case, it's going to remain the same, just to be 1. Right? But I'm still going to highlight it just to make sure you understand exactly what's going on by using a skip. Skip is conceptually a very simple event, but it's so fundamental whenever you want to prove the refinement for the newly introduced events in the refinement model. All right? Alrighty, so before we check that, let me highlight it. So this will be the concrete events that's new, and also this part here is the corresponding abstract counterpart, the dummy events. Now we should do the final most important check, which is to make sure the resulting states from the ILM and also the resulting states from the corresponding abstract counterpart, which is dummy events, the resulting states over here, these two, are still related to by the invariant number 4, the concrete invariant. That's the most important thing to check, right? We want to make sure this event here is really simulated by this event, because the only way to check it would be to make sure the corresponding post states over here can still be related by the same concrete invariance, invariant number 4. It's a very important big picture for you to understand why what kind of exercise we're doing over here. Right, so let's now still try to use purple over here just to make sure this concrete post states can still be related to the abstract post states over here. And the concrete invariance we have is invariance for model 1, number 4. The post states A prime plus B prime plus C prime is equal to N prime. Of course, if we only talk about this particular transition, this part here will be the pre-states, and this will be the post-states. When we spoke about this particular transition, this will be the pre-states, and this will be the post-states, meaning that these two states over here can either be treated as pre-state or post-state, depending on which transition you're talking about, right? That's something I want to say as well. So these two will be treated as post-states if we are talking about this transition. They will be treated as pre-states if we are talking about this transition, just to be very precise. All right. Let's now check with the invariance quickly, right? So you can see n prime over here. Let me write it down. N prime is simply just 1. Agree? Over here. What about A prime plus B prime plus C prime? 0 plus 1 plus 0. There will still be 1. So this concrete invariance indeed is maintained. You can see we can verify this by simulation, by kind of like executing the machine on the paper, right? So let me do a final highlights, and then we're done for this part. I think it's really important, before we actually formulate the sequence, to really understand exactly what we're really doing here, especially with the new idea about this particular dummy event, skip, for the newly introduced concrete events to be simulated, right? Let me just do a final highlights about what exactly the exercise was focusing on. So it would be about this pair of transitions over here, right? So just make sure you stay focused about exactly what's being illustrated over here as the new stuff. Alrighty, so let's now move on to the next part, which is about to formulate the sequence related to the invariant preservation of the newly introduced events in the refinements.